So this is about metallic bonding. First of all, let's look at the definitions. So you can see at the first point here, metal atoms are tightly packed together in lattice structures. So this is the lattice structures. You can see some positive ions with the blue dots, which is the electrons. So the positive and the negative ions are attracting each other. That is the metallic bond. The lattice structures that they show that they mean here is actually the repeating of the positive and the negative electrons. So the positive cations of the metal and the negatively charged electrons, they keep repeating throughout the whole structures. So we call that lattice structures. So example, let's say sodium. Okay, so sodium, they will change to sodium plus and electrons. Okay, so after that, the electron can move any way they like. So we call that delocalized. So they can move anywhere. No need to stick to the original master. So it gets its freedom. So can move anyway. So then they form the lattice structures in that way. So the positive refer to the Na plus. The blue dot is the electrons. Okay, now let's see the second point here. When the metal atoms are in lattice structures, the electrons in their outer shells are free to move throughout the structures. So the electrons in the outer shell means the valence electrons are free to move. Okay, so for example, sodium, 1 valence electrons. But if let's say I have calcium, so calcium, then you should expect calcium to have 2 electrons that are free to move when they stay in the lattice structures. So the free moving electrons are called delocalized electrons. Okay, delocalized. So that means they are not going to stick to their original master. They can move anyway, and they are not bound to their atoms anymore. So because of that, because of delocalized electrons, then metal can carry electricity or can carry current. Okay, so when the electrons are delocalized, the metal atoms become positively charged, as in here, positively charged, and these are free to move any way they like. And then the positive charges repel each other and keep the neatly arranged lattice in place. So it's like this. They are tidied up in that way. And there are very strong forces between the positive metal centers and the sea of delocalized electrons. Okay, so that is the metallic bond. It's the attraction between the cations and the delocalized electrons. Okay, now you can see here, when metals are closely packed in a lattice, their outer electrons dissociates from the positive center. So something like this, delocalized. You know, initially this picture showed that the electron are still at the outer shells. It's not delocalized yet. So when they are delocalized, they are no more at the shells. They are free to move any way they like. And you can see here. So once the outer electrons are delocalized, the positive metal centers are suspended in the sea of electrons. So imagine all these are in the sea of electrons. So imagine you put them in water. Okay, so they arrange themselves in this way. These are like the stones. Imagine stone in the sea. So the stone arrange themselves neatly, and it is surrounded by water. Something like that. So metallic bonding is the strong electrostatic forces. So you hear these electrostatic forces again. So meaning that is between the positive and the negative ions that attract each other. So this is the attractions, metallic bond, positive and negative. Okay, let's move on. Okay, so that's all about metallic bond. It's quite short. Covalent bond is the one that is long. Okay, so covalent bonding, let's take a look. First, let's see the definitions. Covalent bonding occurs between two nonmetals. Okay, so for example, it's like oxygen molecule, so O2, or another example, chlorine. Okay, so these are covalent bonds, or maybe another example, water. Okay, then second point, a covalent bond involves the electrostatic attractions between nuclei of two atoms and the bonding electrons of their outer shells. So again, you can see electrostatic attraction again. So that means positive attract to negative, and then that is called electrostatic attraction. So how is it? You can see it in this way. So the positive attracted to the negative attracted to the positive. So that is covalent bond. You have positive, negative, and positive that attract each other. And no electrons are transferred, but only shared in this type of bonding. So ionic bond, they transfer electrons, but covalent bond, they share electrons. And then let's see here. Non-metals are able to share pairs of electrons to form different types of covalent bonds. Okay, so non-metal, like oxygen, they are non-metal. H2O, non-metals. So they share electrons. Sharing electrons in the covalent bond allow each of the two atoms to achieve an electron configuration similar to a noble gas. So we call that octet. Okay, octet. O-C-T-E-T. Octet. So octet means 8 electron at the outer shell, or duplet. Duplet means 2 electrons at the outer shell. So these are the electronic configurations of the noble gas. So this makes each atom more stable. Okay, and then covalent bonds, we have single covalent bond, so they share 2 electrons. Double covalent bond shares 4, and you can see 2 lines. Triple bond shares 6 electrons. Okay, let's move on. And here we have dot and cross diagram. So dot and cross diagrams are used to represent covalent bonding. So this is the example. You can see hydrogen's molecule here. So one of the hydrogen atom use cross, another hydrogen use dot. So we call it dot and cross diagram. That shows just the outer shells of the atoms involved. So that means, let's say for example, like chlorine, Cl, Cl. Okay, so let's say this is the shell. We don't show the inner shell of 2 electron and then the second shell of 8 electron. We just show the third shell of 7 electron in this particular way. Dot and cross. 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4. Okay, so this is the example, dot and cross diagram. Of course, they show us the more basic example here. Okay, so to differentiate between the two atoms involved, dot for electrons of one atom and crosses for electrons of the other atoms are used. So you can see dot for this and then crosses for this. And then electrons are shown in pairs on dot and cross diagrams. Okay, show in pairs. So that means like 2 here, 2 here, 2 here, and 2 there. Okay, so single covalent bond, hydrogen's molecule. So this is the case. Initially they are atoms. So after that, they form covalent bond that share 2 electrons. So sharing 2 electrons is single covalent bond. Okay, now let's move on. So on this page you have more example. So you can see chlorine molecule. Just now I discussed with you. So you can see 7 valence electron with 7 valence electrons. So after sharing, they achieve the electronic configuration of noble gas. You can see this one has A, this one also has A. Okay, and then hydrogen chloride. So hydrogen chloride, you can see hydrogen has 1 electron, this one has 7. So when they share, something like this happen. So hydrogen gas form duplet, 2 valence electron in the first shell. So 1s2, so that is duplet. So this one form octet. Okay? So it happens in this way sometimes. So one take duplet, another one take octet. Okay, so let's move on. You can see ammonia here, NH3 ammonia. So what happened is sometimes when they form covalent molecules, so they form single bond with this, single bond with this, and single bond with that, and we still have lone pair over here, lone pair. Okay, so this is the extra electrons which is not going to form any bonds. So you may also write like this. You can see the lone pair in this way. And then we have the next one, methane. Methane is one carbon with 4 hydrogens, so they form 4 single covalent bond as in here. Okay, so it's 4 single covalent bonds. And more example, ethane. So ethane is C2H6. So you can see the carbon here, 1 2 3 4, 4 single bonds, and this carbon also 1 2 3 4, 4 single bonds. So they form something like this. Okay, and let's move on. Okay, now double covalent bond. So first we have oxygen. So many students are wondering how I know they form double, or how I know they form single, or maybe even triple, how I know whether they are going to form double. So let's say, for example, how we know oxygens form double. Of course, the idea is to form covalent bond, right? They try to make themselves to have 8 electrons, or electronic configuration of noble gas. So they are having 6 electrons now. You see 1 2 3 4 5 6. So to get 8 electrons, they need 2 more. This oxygen also, they need 2 more. So if this is lack of 2, this is lack of 2, so the only way to do it is they need to share 2 electrons between them. So this oxygen share 2 electrons, this oxygen also share 2 electrons. At the end, both will have the octet arrangement. So as you can see, 1 2 3 4 5 6 7 8 for this oxygen. Even for the oxygen on the right, 1 2 3 4 5 6 7 8. So both achieve octet. Okay, now let's see carbon dioxide. Carbon dioxide, they form double bond also in this particular way. So you see carbon, right? So first you think about it in this way. Carbon need 4 electrons to achieve octet. Oxygen need 2. This oxygen also need 2. So if they need 2, they will form double bond. If they need 1, they will form single bond. Basically it's like that. So if they need 2, then this 2 is given to this. These 2 are given to this. So they will have double bond in this way. Double bond and double bond. So this is the way. Okay. Carbon dioxide. And now let's see more example. This is the alkene, which is known as ethene. Ethene C2H4. Okay, C2H4. So when they have C2H4, that means 2 carbon, 4 hydrogen. Hydrogens always form single bonds. So you see there are lack of 1 to achieve the 1s2. So the lack of 1, they share 1, share 1, share 1, and share 1. So after that, this is what we call duplet. Noble electronic arrangement of helium. Okay, helium. So same like helium. Helium also two electrons. So the carbon, after sharing one electron with these two, so this carbon still have two more. Okay, so still have two more, and then they share with the other carbon. So here is where they form the double bond. So you can see here, carbon-carbon double bond, and then the rest are single bonds. Okay, then let's see, triple covalent bond. So triple covalent bond, the idea is the atom itself lack of 3 electrons. So if they lack of 3 electrons, then they will share 3 electrons with others to form triple bonds. Okay, as you can see here, nitrogen has 5 electrons, lack of 3 to become octet, lack of 3. So they put 3 electrons in the middle to be shared. So this nitrogen also put 3 in the middle to be shared. So at the end, they both have 8 electrons. 6 here and 2 here. 6 plus 2 is 8. 6 here and 2 over there. So it's also 8. So triple bond. Okay, now let's see. In some instances, the central atom of a covalently bonded molecule can accommodate more or less than 8 electrons in its outer shell. Okay, so this is the example. You can see sulfur. Sulfur at the end, after forming the covalent molecule, you can see 4 plus 4 plus 2, that is 10 electrons in its outer shell, which is known as expanding the octet rule. So who can do this? Of course, not all the elements can do this. There is a condition. It has to be period 3 onwards. Period 1 and period 2 cannot do expanding, cannot have the expanded octet. So only period 3 onwards can do that, because period 3 has 3d orbital to accommodate more than 8 electrons. Okay, so being able to accommodate more than 8 electrons in the outer shell is known as expanding the octet rule. Accommodating less than 8 electrons in the outer shell means that the central atom is electron deficient. Okay, so let's put more explanation on this thing. This is the central atoms. So these two are the terminal atoms. Terminal atoms, right? The rule is they must achieve octet. Terminal must achieve octet. But the central can be octet, can be more than 8, can be less than 8. Okay, so remember that. Yeah, this is terminal. Terminal atoms are basically the atoms that is not in the middle. So this one must be octet. And this is the central. Central, you have 3 options: octet, or more than 8 or less than 8. Okay, so maybe I put like this: equal to 8, more than 8, or less than 8. Okay, so 3 options here. Okay, this is the example. And let's see, some example of this occurring can be seen with period 3 elements. So this is period 3. Okay, so they form this 10 electrons. So sulfur dioxide look like this. Okay, let's move on. The next one is PCl5, which is phosphorus pentachloride, PCl5. So this phosphorus, you have to know that it is staying at the third period. So it can have the expanded octet, which means more than 8, because it has 3 d orbitals to do that. So they can take 5 chlorine, 1, 2, 3, 4, 5, and form 5 single bonds. So altogether, phosphorus has 10 electrons. But you see the terminal atoms here, the terminal atoms, they all have 8 electrons. Okay, so this is again the this is what we call the expanded octet. Okay, then again, one more example. So you can see for this case, sulfur, 6 valence electrons. The fluorine here, they have 7, they are lack of 1, so they need 1 electron each. So 6 of them, you get 1 electron each from 6 of the electrons here, and they form something like that. Again, you can see sulfur can take 12 electrons for this case. So this is again expanding the octet loop. Okay, so this is the structures, sulfur hexafluoride. Okay, now exam tips. Covalent bonding takes place between non-metal atoms. And then remember to use the periodic table to decide how many electrons are in the outer shells of a non-metal atom. Okay, so you look at the periodic table, you see how many valence electrons are there, and then after that you can determine how they share electrons with the rules where the terminal atom must achieve octet. The central atoms can be 8, can be more than 8 or less than 8. So it seems like covalent bond we have done, and now we have coordinates bonding. Actually, coordinate bonding is also covalent bond. It's a special kind of covalent bond. Okay, now let's see the details. Okay, dative bonding, or maybe you're wondering, over here they say coordinate bonding, and over here they say dative bonding. So actually these two are the same. Okay, they are the same. So let's start from the basic one. In simple covalent bonds, the two atoms involved shares electrons. Share electron is the fair deal. So if one atom contribute 1, the other atom has to contribute 1 also. If one atom contribute 2, the other atom contribute 2 electrons. So it's a fair deal. Coordinate bonding or dative bonding, they are not fair. They are not fair. Okay, so some molecules have a lone pair of electrons that can be donated to form a bond with an electron deficient atom. So remember, electron deficient means they are not having 8 electrons yet. Okay, so example, let's say aluminium chloride. Aluminium chloride, AlCl3. So you can easily imagine that this is like Al, Cl, Cl, Cl. So 1, 2, 1, 2, 1, 2. So it look like this. The terminal atom, the chlorine, they achieve octet. So each of these has A, and A. But the aluminium, 1, 2, 3, 4, 5, 6. Okay, so 6 electrons for the aluminium. So that is not octet. So we call it electron deficient. So if it is lack of electrons there, so what happens is they can find another atom with lone pair, and they can put the lone pair here. Okay, so for example, chloride can come here. Chloride, okay, let's say chloride. chloride can come here. Chloride, let's say 1, 2, 3, 4, 5, 6, 7, 8. So chloride negative charge. Okay, they can come here. So this is where the dative bond happens here, at this particular place, dative bond. Okay, so dative bond, they must have one party that is lack of electron, another party has lone pair. Okay, so we call it donor, and this is acceptor. Okay, now let's see. An electron deficient atom is an atom that has an unfilled outer orbital. Okay, they still have one empty orbitals to accommodate electron. I mean aluminium. Aluminium has one empty orbital to accommodate the two electrons there. So both electrons are from the same atoms. So the two electrons are from this donor, from the same atoms. This type of bonding is called dative covalent bonding or coordinates bonding. Coordinates bond. Okay, so normally we put like this. We put like aluminium, single bond, single bond, single bond, dative bond. Okay, so this is one way to present it. This and this are the normal covalent bond, and this is the dative bond. It's a special covalent bond or coordinate bond. Okay, so an example of a dative bond is in an ammonium ions. Okay, so let's see the picture at the same time. Ammonium ions, first you need to know it is ammonium ion is NH4 positive. Okay, so NH4 positive, right, is basically because of ammonia and hydrogen ion, as you can see in the picture here. Okay, so we have ammonia. This is the one. Ammonia has lone pair. H plus has no electrons here, so that means the first orbital 1s is not taking any electron. It's 1s0 now, so it can take the two electrons from here, as in here you can see that. You see this one is dot and cross, dot and cross, dot and cross, but this is two crosses, showing that this is the acceptor, lone pair acceptor. This is the lone pair donor. Okay, so this is where they form dative bond. Okay, so the hydrogen ion is electron deficient and has space for two electrons in its shell. The 1s can take two electrons. The nitrogen atom in ammonia has a lone pair. This is the lone pair, which it can donate to the hydrogen ions to form a dative covalent bond. So dative covalent bond is here. Okay. Then sometimes you may see the draw like this: N, H, 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 and then arrow H plus. Okay. So, and sometimes you may see the draw like this. They don't want to see any difference between the dative bond and the simple covalent bond. They just put like this. It is okay. Okay, so we can put like this because after they form the dative bond, right, basically they have the same properties with the normal covalent bond. So the dative bond has the same properties with the normal covalent bond. So at the end they don't want to see the difference, so they put the positive charge outside, and the positive charge is from this, they put outside, and then the rest all show the normal covalent bond. So sometimes it happens in that way. Okay, then this is another example: aluminium chloride. So aluminium chloride is AlCl3. So they say it's also formed during dative is also formed using dative covalent bonding. At high temperature, aluminium chloride can exist as a monomer. Monomer means one unit. AlCl3 is considered a monomer, which is considered one single unit of molecule. So the molecule is electron deficient, as we discussed before. They have only 6 valence electrons and need two electron. Need to what English word is this? Need two electrons complete. Okay, so need two electrons to complete the aluminium atoms outer shells. So I put it in that way. Okay, so at lower temperatures, the two molecules of aluminum chloride join together to form a dimer. Al2Cl6. So dimer is what? Dimer is like two monomers that join up to form dimer. Okay, so to form dimer, they are more stable to exist in this form rather than this form. This form is happening when the temperature is high. Okay, it's like 700 something degrees Celsius. Then they will have these structures. So if the temperature is lower than that, then they will form dimer. So the molecule combine because lone pair of electrons on two of the chlorine atoms form two coordinate bonding with the aluminium atoms. So let's see how it works. So you can see the picture here. We look at this one first. This is the simple structures. Okay, I put two circles for our reference here. This is one monomer. And this is another monomer. Okay, so you can see they join up by using dative bond. So where's the dative bond? This is the first one. The lone pair of the Cl is given to the aluminium here, one dative bond. So this one, the lone pair of this Cl is given to the aluminium also. So two dative bond. Okay, and the rest are the normal covalent bond. So there are 3 normal covalent bond and one dative bond. This is the special one. So as you can see here, normal. This is the dative bond. The lone pair are from chlorine to the aluminium. So this is the other monomer. So normal covalent bond. This is the normal one, normal, and this is the dative. The dative one.
So yeah. How do we know that it will form a dative bond?
Basically, they form dative bond when there is an electron deficient. That is the first thing. Electron deficient. So one of the molecule must be electron deficient, and the other atoms has lone pair, for example, and then they will form dative bond.
Cause like just now we did like the covalent bonding, and then it was like PCl6, I think, cause like the phosphorus still had lone pairs. But is it because that one was like the center was already full, and for this one like the center is not full?
Okay, what you mean just now is the PCl5, right? We have PCl5. This PCl5, they don't form dative bond because basically they form 1, 2, 3, 4, 5. They form 5 5 single covalent bond. They don't form dative. Okay, so here they form dative. Why? Because somebody has no 8 electrons. Okay, and that is the first condition. Somebody do not have octet electrons. They are lack of electrons. We call it electron deficient. So must have somebody that are lack of electron and somebody that are having lone pair. Then dative covalent bond or dative bond or coordinate bond is formed. Okay, must have that condition. This one is different, this one nobody has electron deficient. So as you can see, this one has, sorry, it's not. This chlorine 8, and 8. This phosphorus has 10, so they are not lack of that. Lack of electrons or electron deficient is less than 8, So none of them have that problem. So they don't form coordinate bond. Okay, so my suggestion, you try to remember it. Who form coordinate bond in our syllabus? NH4 plus Al2Cl6. So these two are the molecules or the examples that form coordinate bond. Yeah. So why they form? Because somebody is lack of electron. Who is lack of electron? So H plus, lack of electron. And then NH3 has lone pair. So this one, who is lack of electron? AlCl3. So the Al is lack of electrons. This is lack of electron. And then the other one is also AlCl3. This AlCl3, the Al is still lack of electron, but the Cl has lone pair. So that's why the lone pair form dative bond with this, the lone pair form dative bond with that. So they are like making each other complete. Okay, so let's see whether they give more example or not. No more already. Okay, so you can see that the exam tips here. In dative covalent bonding, both electrons in the covalent bond are shared by one atom. Okay, so that means one of the atom give the lone pair. Okay, give the lone pair. Both electrons in the covalent bond are shared by one atom, and another atoms has electron deficient, so that they take the lone pair. So a dative covalent bond uses an arrow from the donated pair of electrons to the electron deficient atom. So you remember these two first as your example, which is ammonium ion and the dimer aluminium chloride. So that will be your example to form the dative bond. Okay, so let's see hybridization. So what is hybridization? Maybe you heard of hybrid car. Hybrid car is like they mix between petrol as the source of energy and electric as the source of energy. They have two sources of energy. Okay, so they mix. That means hybridization is about mixing. So what are they going to mix here in covalent bonding? So the orbitals are going to mix in a particular way. So you see how bond overlapped in covalent bonds. A single covalent bond is formed when two non-metal combine. Okay, so for example, like two non-metal, let's say chlorine and chlorine. chlorine and chlorine. They combine. They form a single covalent bond. They share electrons. So each atom that combine has an atomic orbital containing a single unpaired electron. Okay, let's see. Chlorine. Chlorine 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so the orbitals in front are all fully occupied except the last one. So let me draw out the diagram for the last one. 1, 2, 3, 4, 5. Okay, so the statement here that mentioned there is a single unpaired electron. So this is the unpaired electron, this one. Unpaired electrons. Okay, so what happened then? Let's see the next point. When a covalent bond is formed, the atomic orbital overlap to form a combined orbital containing 2 electrons. So they overlap. Okay, they overlap. So that means this unpaired electrons orbital is overlap with the unpaired electrons orbital for another chlorine atoms. Okay, so meaning that, imagine you have another chlorine, you have 2p5 also, 1, 2, 3, 4, 5. Okay, so this one has unpaired electron as well. So these two overlap. And they overlap. So when they overlap, we call it combined orbital and containing 2 electrons. Imagine this and this combined already, so it has 2 electrons now. And this new orbital is called the molecular orbital. Okay, molecular orbital. So after they overlap, then we call it molecular orbital. Before they overlap, they are atomic orbital. After they overlap, they form molecules, so we call it molecular orbital. Before these two join up, they are atoms, so we call it atomic orbital. So the greater the atomic orbital overlap, the stronger the bond. So we have two situations. So the first situation is sigma bond, the second situation is pi bond. Sigma bond has more overlapping, pi bond has less overlapping. So sigma bond are formed by direct overlap of orbitals between the bonding atoms. So what is meant by direct overlap? In terms of picture, it is like this. For example, H2. H2 is hydrogen and hydrogen. Hydrogen, you know, there are 1s1 and 1s1. Okay, so 1s1, the orbital is a sphere shaped, so overlap with a sphere shaped. Okay, so this is where the atomic orbital overlap, and they overlap in this way. This is direct overlap. So another example is like HCl. So this one 1s1, this one 1s2, 2s2, 2p6, 3s2, 3p5. So the Cl, like what we discussed, they use this orbital to overlap with the 1s1 orbital. This one has unpaired here, and the 3p5 has the last orbital that has unpaired electron that overlap. So when they overlap, we draw like this. This is for the 1s. And for chlorine, you know, this is p orbital. P orbital is dumbbell shape. So dumbbell shape is going to be like this. Okay, so they overlap in this way. So this is called direct overlap. Chlorine and chlorine, for example, chlorine and chlorine is the p orbital overlap with the p orbital. So the picture is going to be like this. Is one dumbbell overlap with another dumbbell. P and P overlap. So all these are direct overlap. Okay, so which means so far we have 3 direct overlap. This is the first, this is the second, this is the third. Direct overlap form sigma bond. Sigma bond involve hybridization, just for your information. We will see in details later. But the next one is pi bond. Pi bond are formed by the sideway overlap of adjacent above and below the sigma bond. When are they going to form pi bond? They form pi bond in double bond and triple bond. So let's say, for example, carbon double bond with carbon. So one of the bond is sigma, another bond is going to be pi. Triple bond. One of the bond is sigma, the other two is going to be the pi bond. The idea is sigma bond must be there as the basic structures. So after that, if they need more than sigma, more than single bond, then they will start to build up pi bond.
So yeah. Is hybridization only in like when the orbital has one unpaired electron? So like can it not happen if it's 3p3?
3p3. 3p3 cannot already. So it's full.
So it has to be like one like 3d9 or like 3p5.
Yeah. 3d9, yes. 3d5 also, they have unpaired electron. Yeah, then it's possible. Maybe I should make it easier for you in this way. If you found the molecule to have single covalent bond, then you have to know that all those single covalent bond are sigma bonds. Okay, sigma bond. For example, CH4. You can see 4 single covalent bond. So I have to say that all these are sigma bond. Okay, so there are 4 sigma bond there. So 4 sigma bond. And maybe you are wondering, has unpaired electrons. Is carbon having 4 sigma bonds? So maybe you are wondering on that. Okay? Because to form 4 sigma bond, so carbon should have 4 unpaired electrons. So let's see carbon. Carbon is 1s2, 2s2, and 2p2. This is carbon. So if I draw out the orbital diagrams, 1s2, 2s2, 2p2. So you will realize that this is only 2 unpaired electrons. How are they going to form 4 sigma bond? So we have to take this as ground state. This is ground state. Ground state means they are at the lowest energy. They don't have enough energy to form covalent bond yet. So they are having the lowest possible energy. Now, in order to form covalent bond, they need to go to excited state. So they need to absorb energy. Then the carbon in excited state will look like this. 1s2. Okay, so when they absorb energy, right, basically what happens is one of the electron here is going to here. One of the electrons absorb energy and come here. Okay, so now it has we have 4 unpaired electrons here. So this is called the excited state. Excited state. Now when they are at the excited state at this moment, so in order to form 4 sigma bond, they need to go through hybridization. Okay, hybridization. The next step is hybridization, which means mix together. So they mix together in this way. Okay, let me draw out. The 1s2 remain, but the 2s2, I mean the 2s and the 2p orbitals, they are going to mix together like this. Something like this. Okay, so this is where the orbitals hybridize. As you can see, 4 of these, they hybridize, and after that, each of these will form 1 sigma bond with 1 hydrogen. So this one will form 1 sigma with hydrogen, 1 sigma with hydrogen, 1 sigma with hydrogen, 1 sigma with hydrogens. So altogether, they form 4 sigma bonds. Okay? So this is one example. Remember the idea? The process is seems to be quite complicated. The concept can be taken easily in this way. If there are single bond, sigma bond is there. Sigma bond, hybridization happen. If they have pi bond, that means they are forming multiple bond, like double bond or triple bonds. Okay, so let's see the next page. Maybe they have more explanation. Okay, let's see here. Sigma bond. Okay, so you can see sigma bond are formed from the end-on overlap, or we call it head-on overlap of atomic orbitals. So s orbitals overlap this way, as well as p orbitals. So the end-on overlap is like what I draw just now. A sphere with a sphere, or a sphere with a dumbbell, or a dumbbell with a dumbbell. That is the end-on overlap. Okay, so what they show here is s orbital that overlap. So when they overlap, initially they are like this, then they overlap, then after that they form something like this. Okay, so this is atomic orbital, this is where they overlap, this is called molecular orbital, then they form the sigma bond. Okay, so example is hydrogen, hydrogen, now they overlap, now they become molecules. Okay, so let's see here. The electron density in a sigma bond is symmetrical about a line joining the nuclei of the atoms forming the bond. Okay, so meaning that the electron's density is the same everywhere around here. The orange color region is where the electrons are free to move. The pair of electrons is found between the nuclei of the two atoms. So that means these are the two nuclei, the nucleus. Okay, and then electrons are mostly staying here in between. So that positive attract with negative, negative attract with positive. So the electrostatic attraction between the electron and nuclei bonds the atoms to each other. So I think they don't highlight one important thing here. Sigma bond, when they form single bond, then that is sigma bond. Okay, so example for this case, H and H, you can see, okay, this is single bond, then it is sigma bond. So this is sigma bond. Okay, more example, HCl, single bond, so this is sigma bond. Easier to take it in that way. Cl and Cl, single bond, and this is sigma bond. Okay, so just now I also give one example. This one, 4 single bond, then 4 sigma bond. So sigma bond happens in single covalent bond, and that is sigma bond. Okay, now pi bond. So pi bond, before we look at the information here first, let's see example. Pi bond is happening in multiple bond. So 1 sigma, 1 pi. Triple bond, 1 sigma, 2 pi. Let's say nitrogen, 1 sigma and 2 pi. So you see they always need 1 sigma as the basic structures, then the rest will be pi. So carbon dioxide, 1 sigma, 1 sigma, and then the other one pi. Oxygen, 1 sigma, and then pi. So you should observe something. Pi bond happens in double bond and triple bonds. If the molecule has single bond, then it is always sigma bond. Sigma bond, hybridization happens. Pi bond, no hybridization. We will discuss that later. And let's see information over here first. So pi bonds are formed from the sideway overlap of adjacent p orbital. Okay, so let's say I draw out a picture to let you see how they have the sideway overlap. Okay, I use oxygen as my example. So you know oxygen is 1s2, 2s2, and 2p4. Okay, so 1 2 1 2 1 2 3 4. Okay, so oxygen look like this, and now another oxygen will look like this also. So these two oxygen atom is going to form 1 sigma bond and 1 pi bond. Yeah, 1 sigma and 1 pi. So it will form something like this. Okay, it will form something like this. This is the dot and cross diagram. So let's see the oxygen on the left. They have 2 lone pair, 1 pair, second pair, and then they share 2 electrons to form the double bond. Okay, so 1 lone pair, 2 lone pair. These are the 2 lone pairs, and then 2 of these are going to be used to form the double bond. Okay, so they have to form 1 sigma bond. 1 sigma bond. They have to form 1 sigma bond and 1 pi bond. Okay, 1 pi bond. So they are going to do hybridization in this way first. Are they going to do any excited state or not? Actually no need, because the electron here is already just nice. Okay, we have 2 unpaired electrons to form 2 bonds. That is just nice. No need to shift any electron to the higher level. So that is not necessary. Some more we need these two as the lone pair. So we don't want to shift any electron to the higher level. This is the ground state itself is just nice. So no need to go to excited state. So we can do hybridization straight away in this way. Okay, so hybridization. How they do hybridization? If you see there are one pi bond, so you remain one for pi bond. Don't hybridize this. You know pi bond that don't hybridize. So only sigma bond hybridize. This is going to form the sigma bond. Okay. So you remember it in this way. This is the lone pair. So which is lone pair here and lone pair here. Okay, and then this one, they form the sigma bond. And then this one, they form the pi bond. Okay, this is the pi bond, let's say. Okay, now lone pair and sigma bond will hybridize. Pi bond don't hybridize. So which means we do like this. This one hybridize. Okay, so hybridize, and this one is unhybridized. So the hybridized will form lone pair plus sigma. It is going to be lone pair plus sigma bond, and this one will form the pi bond. Okay, so after that, they form the molecule in this way. Okay, so this lone pair, yeah, this lone pair, yeah, this one will form sigma bond with another oxygen atom. This one will form pi bond with another oxygen. So how it looks like, let's say I draw out. The diagram will be more complicated. Okay, so first you need to know this is the p orbital. So p orbital is dumbbell shaped. After hybridized, the dumbbell shape look a little bit different, like this. Okay, so this is one of the, this dumbbell shape, right? This shape is because of this. Okay, the unhybridized will look like the normal dumbbell shapes. Okay, let's say I use green color, the normal dumbbell shapes.
Okay.
Yeah, something like this. Okay, the nucleus is here. The nucleus is in the middle. So this is one oxygen atom. One oxygen atom. Another oxygen atom will be like this. They have a similar situation. The other oxygen atoms, they also have one orbital that has been hybridized. Okay, so which is this one. And then one more is unhybridized. It looks like this. Okay, so the sigma bond is here. This is the sigma bond. They have the end-to-end overlap or head-on overlap. The pi bond is here. Sideway overlap here also. Okay, let me purposely make them overlap in this way. So I want you to see their overlap obviously. So I purposely make my round shapes overlap. Okay, so you can see so this is the place where they overlap. They overlap here and here. Okay, so they overlap there. So this is where they form the pi bond. So pi bond. So pi bond is formed over here. And here. That's the pi bond. That is one pi bond. This is where they form the sigma bond. It looks like that. Okay. So maybe you're wondering, how about the lone pair? The lone pair, they are hybridized also. You see there are lone pair here and lone pair here, so they are hybridized also. They will form a structure like that. So the lone pair, another structure like this. Okay, very complicated. Here, lone pair, and here, lone pair. Okay, so that is how it looks like. It is more complicated compared to the dot and cross diagram. So you try to compare. So this oxygen is here, the nucleus is here. So the pi bond is here, the sigma bond is here, the two lone pairs here and here. Okay, so this oxygen atom same also, one sigma, one pi, two lone pair. So this oxygen atoms, the nucleus is here, the sigma bond, the pi bond is up and down, the lone pair are here. Okay, so quite complicated, I guess, when you look at this. Yeah. Now, let's see the information and the picture at the same time. Okay, so you see the information here. Pi bond are formed from the sideway overlap of adjacent p orbital. So here, sideway overlap. The two lobes that make up the pi bond lie above and below the plane. So you see, lie above the plane, below the plane. The plane is here. Imagine three of these lies on a flat surface, lie on a horizontal surface. Something like this. This one is 3D already. Something like this. Okay. Then this is the rectangle that I show the horizontal surface where this and this lies over there. And then the green one, they are like up and down. Up and down. Okay, so imagine. And let's see the next point. This maximizes overlap of the p orbitals. So here and here, the overlap. A single pi bond is drawn as two electron clouds, one arising from each lobe of the p orbital. Okay, so this is one loop. This is also one loop. So there are two electron clouds. This is one electron cloud. This is the second electron cloud. And the two clouds of electron in a pi bond represent one bond containing two electrons. So two electron clouds, but only one pi bond. So they are trying to say something like that. Okay, and let's see the next point, the next page. Okay, so they give they give pictures. Their pictures is simplified in this way. As you can see, this is the sideway overlap. Okay, then the overlap sideway, and at the end it becomes like this. Okay, so let's see examples. Sigma and pi bonds. So hydrogens, okay, they form sigma bond or pi bonds is very easy to decide. You know hydrogen is H2. Hydrogen is single bond. It's taking single bond. So this is going to be sigma bond. Okay, so hydrogen atom has only one s orbital. So you can see here, s orbital. So sigma bond. The s orbital of the two hydrogen atoms will overlap to form a sigma bond. Sigma bond. So because this is single bond, so that's why they are sigma bond. So they are taking direct overlap. So which means they are going to overlap like this. Overlap like this. Direct overlap. Okay, now next one. Ethene. So ethene, you know, is alkene, C2H4. My suggestion, you draw out first. And you have to know that single bond are sigma bond. Double bond is where you have one sigma and one pi. Okay, so now let's see. Each carbon atom uses 3 of its 4 electrons to form sigma bonds. So 1 sigma, 2 sigma, and 3 sigma. Okay, another one form pi bond. 2 sigma bond are formed with the hydrogen atoms. So you can see here, 1 sigma with this hydrogen, another sigma with this hydrogen. 1 sigma bond is formed with the other carbon atoms, which is here. So altogether 3 sigma bonds. The 4th electrons from each carbon atom occupies the p orbitals, which overlap sideways. So here, this is the pi bond. The 4th electrons overlap sideways means pi bond. So they are like this. Okay, they are going to overlap sideways, up and down. This is the sigma bond. This is the pi bond. Pi bond is the 2 green color part. That represents 1 pi bond. So this is 1 sigma bond. The second and the third. Okay? So this means that the carbon-carbon is a double bond, 1 sigma and 1 pi. So like what I said, double bond has 1 sigma and 1 pi. Okay, and let's move on. Okay, this is the pictures where it is kind of similar to what I drew just now. This is 1 sigma bond. This is another one, another sigma bond. Hydrogen is, yeah, hydrogen, 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 and hydrogen. So this is the center where the carbon nucleus stay. This is another carbon nucleus. So 2 carbon nuclei. Okay, so one of the electrons is here, the second one is here, the third one is here, the third one. So let's say I put the third one. Okay, the third one. 1, 2, 3. Okay, so you can see 1, 2, 3. 3 electrons are here. The 4th one are here, either up or down. The 4th one. So let's say I just put a cross there. So there are 4 electrons. So 3 forms sigma bond, 1 form pi bond. So likewise for this carbon Okay, let's say this one I use dot. Okay, and then the other one is here, let's say. Okay, and then let's say carbon they have their own hydrogen, you know, C2H4, right? So this is the hydrogen. So hydrogen has electron also. So here, 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 and here. So hydrogen. So you can see the sigma bond. 1 sigma bond, 2 sigma bond, and 3 sigma bond. This is the pi bond. Okay, sigma bond, and sigma bond. So then you can see it in this way. If I simplify it, carbon, sigma bond with hydrogen, sigma bond with hydrogen, sigma bond with hydrogen, sigma bond with hydrogen, and then one more, let's say in green color, pi bond. Okay, the red one is sigma bond, and the green one is pi bond. So that is ethene. Now they put ethyne. This molecule contain a triple bond. Triple bond, just now we discussed before, 1 sigma bond and 2 pi bond. Okay, so the 2 pi bond is a bit more difficult to draw now because they are at right angle to each other. Okay, so I will look at it whether they draw it or not. If not, then I will show you the pictures. So each carbon atom uses 2 of its 4 electrons to form sigma bonds. Okay, maybe you are wondering how. Okay, I show you the formula first. Ethyne is actually C2H2, and ethyne is C triple bond C, and then hydrogen. So sigma bond. Single covalent bond is always sigma bond, and then here 1 sigma and 2 pi. Okay, so this point they said each carbon atom uses 2 of its 4 electrons to form sigma bond. So you see this carbon, they use 1 electron to form sigma bond here, they use another electron to form sigma bond here. So use 2 electrons, and use another 2 electrons to form pi bond. So 1 sigma bond is formed with the hydrogen atom, this one, and 1 sigma bond is formed with the other carbon atom. So another sigma bond is with the carbon, and then the 2 electrons are used to form 2 pi bonds with the other carbon atoms, 2 pi bond. Okay, so 2 sigma bond and 2 pi bonds. Okay, now let's see the next page. Okay, so yes, they show us the pictures. So luckily there is a picture here. Okay, so I can just explain it straight away. So this N is actually the carbon. It's the carbon. Yeah, carbon. So 1 sigma bond, 2 sigma bond. Okay, so and then I label it first. Oh, never mind, the label already. So 1 sigma bond is here, another sigma bond is here. Okay, so this is the hydrogens. Hydrogen is here. The other hydrogen is here. So the pi bond, right? The sideway overlap is in this particular way. This and this one. This is 1 pi bond. The horizontal one. You imagine in this way lah. Okay, you imagine in this way. Let's say I draw a horizontal plane. So one of the pi bond is lying horizontal on this rectangle. Sideways overlap. Another pi bond is lying vertical. Sideways overlap. Okay, so they're trying to show that, but it's a bit not clear here. This is the vertical one. So sideways overlap. One pi bond. This is the horizontal lying p orbital. So sideways overlap. Okay, so the red one. So two pi bond are there. Okay, and then at the end, after sideways overlap, the orbitals combine, and now it looks like that. Okay, so kind of complicated actually. I just do some extra notes here. This is actually the carbon. This is the hydrogen and the hydrogen. Okay. So any questions so far?
No.
It's kind of complicated, right? I have to say that it's not that easy. Yes. Okay.
Will I have to draw this in my exams?
No, they don't ask. They don't ask. Huh? So you just try to imagine. Try your best to imagine on what happens. If let's say you really can't imagine, it is still okay. They don't ask. They don't ask. Huh? But if you can understand, it's good. Okay, it's good. Huh? Let's just move on first. Hydrogen cyanide. Okay, let's see. Hydrogen cyanide. First, I just let you know the formula. It is HCN. HCN. So it looks like this. Okay, you can see a single bond here and a triple bond there. Okay, so let me ask you, is this going to be sigma bond or pi bond?
Sigma.
Sigma, yes. Single covalent bond is always sigma. And here, how many sigma and how many pi?
1 sigma, 2 pi.
Okay, yes, that's good enough. 1 sigma and 2 pi. Okay, so let's see the notes here. Hydrogen cyanide contains a triple bond. The triple bond is here. 1 sigma bond is formed between the hydrogen and carbon. Here. Overlap of an sp carbon hybridized orbital with the 1s hydrogen orbital. Maybe you're wondering, what is the sp hybridized orbital? Okay, so let's see. I explain it in this way. You see, carbon is 1s2, 2s2, and 2p2. Okay, then the orbital diagram is like this. 2 electron, 2 electron, and 2 electrons. Okay, so they are like this, and after that they are going to hybridize. They are going to hybridize. So how many of them are going to hybridize? You see how many sigma? If 2 sigma, as you can see here, if they form 2 sigma, 1 sigma, 2 sigma, if 2 sigma, then 2 of them are going to hybridize. 2 of them are going to hybridize. Maybe you are wondering, am I going to do excited state or not? So yes, because no lone pair here, no lone pair. We don't want lone pair. So the 4 electrons are used to form the bond. So none of them are forming lone pair. So the ground state here need to go to excited state. So this is ground state. Now the absorbed energy, and it becomes excited state in this way. 1, 2, 3, 4 here remain. The 1s2 remain. Only the valence shell can do the excited state. So you can see this electron absorb energy and come here. Okay, so this is called excited state. And now you know they are taking 2 sigma bond. So 2 of these are going to combine. We call it hybridize. Hybridize in this way. So this is called sp hybridized orbital. Okay, to form sigma bond. So they are coming from this and this. So they hybridize. The other 2, they remain unhybridized. So this is the unhybridized orbital. So these 2 will form 2 sigma bond. This one will form 2 pi bond. Okay, so it happened to carbon actually, as you can see. Sigma bond, 2 sigma bond and 2 pi bond. Okay, so you can see that there. And okay, we go through until here before we stop our lesson. Okay, so let's see first. 1 sigma bond is formed between the hydrogen and carbon atom. This one. And overlap of an sp carbon hybridized orbital. So which is this one, hybridized orbital. This hybridized orbital will overlap with the hydrogens 1s orbital. So hydrogen use 1s orbital. A second sigma bond is formed between the carbon and nitrogens, as you can see. Carbon, nitrogen, 1 sigma bond. So overlap of an sp carbon hybridized orbital with a p orbital of nitrogens. So this is the second sp hybridized orbital. It's going to overlap with the p orbital of nitrogens. So from the nitrogen, and then the remaining 2 is here. The remaining 2 sets of p orbitals of nitrogen and carbon will overlap to form 2 pi bonds at right angles to each other. So you can see one of the orbitals are vertical, another orbitals are horizontal. They overlap. So the vertical and the vertical overlap sideways to form 1 pi bond, and then the horizontal and the horizontal overlap to form another pi bond. So 2 pi bond. Okay, so then they overlap in that way. Okay, and then that's all. Settle for hydrogen cyanide.